Oh. Well, we're gonna get started working today because it is Monday. And, well, we have work to do, so let's get started on actually working. Let's make sure everything looks like it should. PM. So I got it in there. So let's find out what we got going on. Today we're going to be working on, I think, the camera zoom and all that stuff. What is Steam VR doing? So right now the camera is all sorts of awful, so we need it to be better. So we need to do lots of things to fix that. All sorts of things. So let's see exactly what we have right now for the camera. I just need to open up lots of files. I'm still waking up, so things could be a little bit slow here. So let's see, we've got camera control. So how exactly do we want our camera to move? Well, we probably need a bunch of things, right? Like, if this is our camera, we've got our player here. Well, we want a few things. If our person is going in a certain direction, we want to slowly move the camera over to follow them. Because we want the camera to move at kind of its own speed normally. Like it should follow the player. But then we also need a couple things for it to do. Sorry, I'm not talking a lot. It's more, I'm just thinking. So what do we need it to do? We need to follow the player. We need to lead the player when they're moving quickly in a direction. We need to not be super responsive, as we need to make sure not to make the player sick. We need to not lose the player. So like, player cannot go off screen. So like if the camera is just gosh, if the camera should never have the player go off screen, pretty much regardless. Like it should always snap at least to have the player on screen. Should we have it so the... I mean, I should look at some things. Shouldn't I? Like I should actually just pull up some other speed-based platforming games. Oh man, and I need to get Flash running on one of my browsers if I'm gonna actually take a look at some of these, don't I? Because a lot of speed-based platformers are online Flash games. So let me take a look at some examples. Let me take a look at Fancy Pants Adventures real quick. Because it's a speed-based platformer. So let's see, the camera... The camera does follow, but it kind of reacts later. And it looks like even when you're moving down at a fast speed, it's not actually moving too quickly. It's kind of lagging behind all the motions. Like even when you're falling down, it's trying to keep you in the bottom right or bottom left, pretty much regardless of what you're doing. So let's take some notes. We should keep the player in the bottom of the screen. We shouldn't lead the player in the vertical direction that much at all. And it looks like also there are set piece screens. So it looks kind of like there's a box around where the player should be, you know, on the screen, and maybe it's just trying to keep the player within that box. And then it gets a little bit faster when the player's outside of the box. So maybe all it is just some simple box collision sort of stuff. Yeah, even he's falling straight down and just it did not lead him down. Now here's the other thing, is like, why is the camera not moving to the right and the left and kind of showing off screen? So the camera knows kind of where in the level you can go, it looks like, as well. There's camera geometry. So we should think about that. the camera is actually geometry on the screen, or geometry in the world, it means you cannot move outside of certain areas. So how do they deal with kind of this sort of situation? Well, it's looking like there's definitely some sort of stuff going on here. And I'm wondering exactly how it's being done. Like, is it a ray cast in a direction to see if you can go? No, because otherwise that right there, like, because it knows there's more level over there. So there would have to be some sort of bounds for the camera, you know, kind of laid out throughout the level for this sort of camera work to even be possible. Because the camera has to know, like, that it can't actually go over to the right, and the way it's doing that, it looks like at least, is by, you know, if there's stuff over farther in the level in that direction. So there's definitely like some bounds to the level itself, which it's using. Maybe there's just a box for the whole level itself. Because otherwise, why is the camera going down into some of these areas? Yeah, so they don't really have complex geometry for it. They're just using something simple. Just a big box for the room. Yeah, it looks like it's taking the average velocity over the past X number, like maybe 10 frames or something like that, and it's using that for the camera motion and to lead the player. You know, it's not very responsive. I should just look at some of these things. Because I want to see what it does when you're not moving. So time to actually install Flash. What? So we'll just take a look. Looks like I can't even pull up the game on in modern Flash. It just doesn't work anymore. Wait, it worked. Okay. Let's take a look. So we're not moving, and we look the other way. Like nothing really happens. Oh yeah, it's... So we actually have to kind of look... If I look the other way, it's... Let's just slowly... Is it just based on where you look? Yeah, it looks like it's just real simple. It's just like if you're looking in a certain direction, it's just a look offset based on... Yeah, it's not based on your speed whatsoever. Because I'm going back and forth on that. Alright, so maybe it's best just to keep things simple. And they're not zooming the camera in and out, are they? Like it's just a certain, just a constant camera. Yeah, good job, Firefox. Install all the updates for no damn reason. And if we do zoom, we need to zoom out based on the center of the screen. So, that's what that means at least. Okay. Yeah, so if we do zoom, we also need to apply a translation, which is when you zoom, when you scale up kind of an orthographic picture, it should scale out from the middle instead of scale out from one location. So let's take a look. Basically for our camera, we're going to need kind of these zooming things, and then we need the lead. So lead speed, min and max. Like, it seems like we shouldn't actually be leading all that much based on... It should be like lead based on direction. So we should have kind of an F vector, like, let's see. Yeah, good afternoon, Karakan. It is 2 in the afternoon over here on the West Coast. We're getting back to the camera stuff. That is important. Let's see, camera direction offset should be something that our camera does. This is the direction offset. This is the offset the camera wants based on the direction the player faces. I think you were successful yesterday in making sure Adam actually checked out all this stuff from Perforce. So good job on that, Karakan. If you were responsible for that. He was still having some trouble though. I don't know. I think he just there's something just basic, like he didn't set his workspace. We should actually probably set this up differently here. We should have another little thing. We should probably have a bool that's like use camera direction offset. If we should use our camera direction offset. You confused him with the ground stuff? Oh yeah, basically like he was making a whole bunch of ground that was kind of, you know, on a small scale. It looked kind of jagged like this, and you know, Bitey's running so fast that when he's running along this ground, you know, he just like flies straight off of this thing. You know, and he'll end up in the air. So basically, for the ground, like there needs to be a very concerted effort that if you're actually doing anything that it, you know, looks very smooth in what the collision is. Even if the grass kind of, you know, looks like this, you know, on the ground, like the collision needs to be real nice. Alright, so we have a camera direction offset. Here did all the tiles. Yeah, like we're gonna have to redo those tiles tons of times, and I think we're gonna have to redo them yet again. Because we probably need them all to be the same width and things like that, so that we can compartmentalize. You know, we can kind of, you know, build things that are all nicely different widths, but using components and little chunks that are all the same width. So, you know, we need like a standard tile. If that's 100 width or 50 width or something, it's basically you can't have anything smaller than that, and that's going to be based on a lot of things. And pretty much everything in the game should have that same size as kind of a minimum width, and that way when we actually make an asset or something, it'll behave reliably for the player. And we should position things such that, you know, like if you take a jump and you're jumping across a pit or something, the pit's not an analog pit. It's always going to be like, well, this is a long jump because it's 5 tiles wide. This is a short jump, it's only 3 tiles wide, sort of thing. People don't always perceive that that's how well constructed things look, but they definitely feel it when they're playing. When they're like, well, why couldn't I make that jump? Like I usually make all those. Right, so camera direction offset is a new one. I'm gonna do F vector. It should be 0. It's not a camera direction offset vector. It's a camera direction percent vector. Offset percent. So it's basically like 0, and then maybe we want to be, you know, because we're working in, basically it goes from 0 to 1, so we have 0.5 to deal with, so it should be like 0.25 in the y and like 0.25 in the z, and that would be both negative. In screen space, if it goes from 0 to 1. Yeah. It's usually pretty common sense with those things. It's just you just have to beat it into people. And let's see, use camera direction, offset is true. So I think that's our camera, like we should be able to use that data. Do we have like overall follow speed? We do. So we need to have, based on the velocity of the player, we do want to lead the player based on their velocity. So what we should do is we should have a number of frames that we actually capture an average velocity. So it should be like in 32 would be like smooth velocity frames. And maybe a smooth velocity frame delay. So basically, like, we'll wait. If we had like 15 frames that we were recording, we might take, we might delay by 5 and then take 10 or something. So like, and yeah, smooth velocity frame delay of, let's just say 0. Well, let's just do something simple like 5. Make sure we're actually using our systems. So there's so we should also have like a kind of the follow speed of the camera should probably not be linear. It should probably be exponential. So we need like follow speed max. So should be follow speed linear, linear velocity, and then like follow speed exponent. Follow speed exponent. So follow speed maximum should be something really big, but not just absolutely insane. So the exponent should be pretty small. We should also have a boolean in here if we can lead in the vertical axis. Allow vertical lead. So this should be like, if we should allow vertical lead. Allow vertical lead. So vertical lead should be probably false by default. This defines the maximum speed of the camera. This defines the basic camera speed. This defines the exponent for moving the camera faster based on distance. So I think I don't think we're missing anything here. Like we've got the basic controls, and that should allow us to tune the camera. So now we actually need to go implement all of this. That's what it looks like. So let's compile it and do all that. It's a little bit cold down here. I'm gonna go change that. Alright. Alright. So we're gonna want to calculate every frame our wanted position and width and all this other stuff, and then we want to actually move towards that in a component fashion. So we're gonna want to move our camera to our we're gonna need a lot of little tuning things because they all move at different speeds. So there's gonna be like the camera origin position where the camera should be, and then there should be the offset, and all of those need to move at different speeds relative to each other in different mathematical spaces. So we're going to need an F vector in wanted camera position. We're going to have F vector in wanted camera offset. We're going to have F vector in wanted camera lead offset. I guess velocity. Yeah, we'll just call it lead offset. So we'll have the float wanted camera, we'll just call it zoom, well, width should be fine. I know it's duplicate, but we're gonna kind of duplicate the logic and then like delete everything. So follow speed max. Camera direction offset. Yeah, we should actually call this the camera direction offset, camera lead offset. We're gonna want an F vector for smooth velocity. And do we actually want a T array of previous velocities. So it's like a T array of f vectors, which would be like velocity history. So we then want, for all these, we want the M current camera position, the current camera direction offset, current camera lead offset, the M current camera width. We're going to need the F vector current follow velocity. So we're going to need a function here that's basically like, we should componentize these things. So we should have like determine camera position, then we should have determine camera zoom, I should call it width based on what we're doing. And we're also going to need an F vector, which is like M current camera width offset. Because when we expand the camera, I think we actually need to move the camera as well to keep it centered. So we got position, we've got width, we've got determine camera direction offset. And then we've got determine camera lead. So I think this should be all the components that we need to actually get it. So we'll basically, we can lead the camera by a certain amount, we can zoom the camera in and out, we're going to be able to determine like our directional offsets, and then we should also determine our basic position. So we basically kind of, I think it'll go somewhat like step 1, move the camera to the correct position. Step 2, move it to its current offset. Then it's going to be determine the direction of the camera, and then determine the lead amount of the camera. And then we also probably want like some bounding box within that camera. Hello Ishu. Good afternoon, sir. We are working on the camera. Because we don't want this all flying outside of this bounding box. But I think if we tune things properly, that really won't be an issue. Because we've got camera lead, min, and max. And min and max should actually be percentages. Right now they're absolute values. So lead max should, instead of being like 2000 or something, it should be like, you know, a portion of the screen, I believe. So we should be basing our lead on the size of the screen, not on something else. It's probably the best way to do it. So our lead max would be like a half screen or something maximum, so we'll just put like 2.25 as our camera lead max default. Alright. So basically what this thing is going to do is we're going to call all of this determine camera position velocity and all this stuff right here, and then we're going to call update camera position, and we're separating it all out basically because some of the math could be a little bit weird, so we want to just break it apart so we don't get super confused as to what the hell is going on, and take it one step at a time. You know, get one thing working as we want it first, and then we're going to add another component after it. I guess we already have these components that are separated into just the tick here. So I was kind of already doing it, but yesterday's work for the camera was kind of just, we're kind of exploring and getting some basic stuff set up. It's not the real stuff. The real stuff is what we're doing today. Let's also make a kind of a print camera values helper method for us to help us out. Shit'll get real, that's right. Wanted camera direction offsets. Got the lead offset. We have the camera width. And then the velocity history. We don't need to print that out. So these are the wanted things. We're gonna need the actual values. Camera lead offset is such. The camera width offset is such as well. Pretty relaxed work day. Very good. Alright, the current follow velocity. And the current camera width. And we should actually have an f-vector final camera position value, which we compute basically. Compute final camera position. Position. 4 days straight in front of the computer. I have absolutely no idea what you're talking about, Carrot King. It seems you've met with a terrible fate. I just like how I was playing Battle Brothers yesterday, and one guy came on and was like giving me crap for not streaming coding. He was like, "No, I want to watch a code." I was like, "Well, Jesus, I guess I suck at games." Alright, and compute final camera position is there. So, we should be able to compile this. You at least go outside every other day. Yeah. Why though? Why? Why would you do that? There are bugs out there, you know that. Eat something else than coffee? You don't eat coffee. Like, coffee is like negative calories. Unless you like put a whole bunch of cream in it or whatever. Coffee is not food. Now you can tell I was like super tired yesterday because I went and cooked some food and then I just like, instead of eating it, I just went and fell asleep. I like took a look at it, I was like, I don't know about this. All the brain needs. Alright, alright. So, we're going to determine our basic camera position. So, what we would assume to be is our camera position would be the position of our followed actor. So basically, it would be like if M follow followed actor is equal to null pointer, then our wanted camera position is going to be our current position. Otherwise, our wanted camera position is going to be the basically M followed actor, get actor transform, get translation. And let's see, our camera offset should be so we're going to add our camera offset to it. So the M camera data. Get, well, this is just camera offset. So if M camera data does not equal null pointer, then our wanted position plus equals the camera offset that we have set. So our X is always going to be locked, is what it looks like. So basically we're going to want to say like M wanted camera position dot X equals 0 just at the end. And then we want to, in components, move towards this value based on a speed. So we're going to have like the question is, should we move our camera based on, like, should it be bounded in both axes, or should I bound the speed in the direction of motion? And what would be the difference? The difference would be if you were running down a hill, if you were actually going diagonal, the camera would be better able to keep up with you. Like the speed is basically, if you bind a speed based on its componentized vectors, basically what you get for a velocity, if this is the velocity vectors, is you get a box. And if you bind it by, the actual length, and you do it like that, then what you get is a circle. So the question would be, which one probably feels better for moving the camera around? Well, we're going to try a box. We're going to try this one. So we're going to have X speed and this is Y speed and Z speed. So if M camera data does not equal null pointer, Y speed is going to be in camera. Yeah, that's kind of what I was thinking too, this box. So we're going to do follow speed velocity, and then we're going to need to calculate based on our exponent. So we're going to do Y speed equals, we need the distance between our wanted position and our current position. So we want like F vector wanted to current to wanted, and that's going to be at the M wanted position, wanted camera position, minus the current camera position, which is So we want the y, the absolute value of the y. So we should have a follow speed linear and maybe a follow speed exponent. So we want the camera data follow speed linear multiplied by the fmath abs of the current to wanted dot y. And we'll also add in the exponent, and we want to multiply the exponent by the speed twice. And same with the z here. Yeah, it's something you'll actually see a lot with particle systems in games, is what people will do for particle systems sometimes is they'll spawn a whole bunch of little point particles all over the place, right? And give them like maybe a random, like a random vector to go in. And a lot of the times when people compute that random velocity vector, they just say like, oh, well, the velocity is roll a random number between -1 and 1 and multiply it by our velocity. And they do that for both directions, and you'll see a lot of explosions that are actually square because we have all these point sprites, coming out from the middle, and it'll look like a square. You'll see that a lot in games, and that's usually a sign of somebody who is kind of new to making effects, because what they should be doing is you take a random angle, and then you do sine and cosine multiplied by your velocity, so your explosion looks like a circle with all your little point sprites inside of it. You'll see that all over the place, so you can usually tell kind of who made it. And pretty much everybody in college would have this sort of explosion, and they wouldn't know it until you pointed it out, because it's not always super obvious. We really want it that way. Angles, man, I don't know how they work. Okay, so what we want to do here is basically we want to say our do our math utils again. So we're going to take this is our current, then our wanted, and then our speed. So we get y speed, delta t, and then our y speed.